let's do a couple of squeeze theorem problems here. The limits for both of these are 0. The denominators are going to infinity, and the numerators are not constant, but they are bounded. Both inverse tangent and sine are bounded functions, so they never are approaching infinity or something crazy. So they're not constant, but they kind of act like constants in the sense that the denominator is getting arbitrarily large. So the fraction values will get closer and closer to 0. But that's not math. We have to prove it. And the way we prove it is with the squeeze theorem. And so we're going to start with our numerator, our function that's bounded. And we know that, that sine is bounded between -1 and 1. And then what we're going to try to do is build up the a sub n here. So sine n over 2n, we want to build that up. And so what I'll do is divide all three parts of this by 2n. So I'm trying to create a sub n in the middle here. And then we were going to take the limit as n goes to infinity of all three terms. So we're going to take the limit across the board as n goes to infinity. And what we are going to see is that in the middle, we have exactly what we're trying to figure out. And on the ends, we have limits that are easily evaluated. So the limit on the left side, we have a constant divided by a quantity that's approaching infinity. Similarly on the right, a constant divided by a quantity that's approaching infinity. So those limits are both 0. And then the middle is the same. So now we have that the limit of sine n over 2n as n goes to infinity is trapped between 0 and 0. It's squeezed between 0 and 0. And so that allows us to make our conclusion that the limit as n goes to infinity of sine of n divided by 2n is in fact 0. And we'll use the same logic for this inverse tangent of n over 4n. We will start with the fact that inverse tangent of n is bounded between minus pi over 2 and pi over 2. And it's true here you could use a strict inequality. You could use a less than symbol for both of those. But if we sort of have a little foreshadowing, we see at the end that we want to be trapped between 0 and 0. It's convenient to use a less than or equal to. It's still true. It's less than or equal to pi over 2 and greater than or equal to negative pi over 2. That's still a true statement. And now we want to build up to a sub n. So we're going to divide through by 4n. So on the left, in the middle, and on the right, we'll divide through by 4n. And then we're going to take the limit across the board. We're going to take the limit as n goes to infinity of all three parts here. And we are going to see the same pattern that we saw above, that in the middle we have the limit of a sub n, and on the right and on the left we have the limit of an expression that's easily evaluated. So on both the left and the right, we're taking limits of constants divided by expressions going to infinity. And we know that that basic limit is 0. If the numerator is constant and the denominator is growing without bound, the fractions are getting closer and closer to 0. And so this is the mathematical justification to make the conclusion that the limit of arctan n over 4n as n goes to infinity is in fact 0.